everyone. This is Professor Namita Bhatt, Assistant Professor, Department of Computer Science and Engineering. I feel privileged to introduce the most dynamic speaker, Mr. Kumar Anirudha, who will be delivering the session on shared security in decentralized apps. He has pursued his BTech from Jalpaiguri Government Engineering College in the year 2014. He was the founding team member of Coders Club JGEC from 2012 to 2014. He was also the secretary of Literary Society JGEC. He has worked as a developer at Proven Logic and Opinio. He was a co-founder of Konoho Technologies. He has worked as senior developer at Skillenza and senior software engineer at Apna. He is the co-founder of Acyclic Labs and Blockchain India. He has been working as a developer advocate at IOTA since 2021. He is also a steering committee member of IEN since 2017. With this brief introduction, I present before you Mr. Kumar Anirudha. Over to you, sir.
Hello, and thanks for the kind introduction. So let's actually get started. Before we dive into this shared security and decentralized apps, I would love to understand how many of you I assume that a lot of you know the basics of what blockchain and decentralized technology is. So if you can just do, can we do a show of not obviously possible show of hands, but you can put it in the chat if you're comfortable with the basics around blockchain and decentralized apps, and then we can proceed, or I can probably cover that part as well. While waiting for that, if you can probably put it in the chat, I guess. While waiting for that, shared security is actually a very active research topic right now. So even in the decentralized sector, this is not a very solved scenario. So people are still working on it. There are various solutions out there, which we will also go through one by one. And but this is obviously not solved. So this is still a very active research topic. And I would, if any of you are interested to work more on it, I would really encourage any of you to go ahead and work on it, because obviously most of the work I have seen being done in the shared security space is from outside of India, and there's very, very less people that I know of, at least working in this space. With that, we can actually get started. I think you heard most of what I have been up to from the kind introduction, but just to cover a particular topics. I've been working with blockchain since 2016, and we founded Blockchain India, which is a blockchain community, and currently the largest blockchain community in the country. We have 4 active chapters: Delhi, Mumbai, Bangalore, and Hyderabad. And after that, founded Acyclic Labs, where we work on as a research and development studios. We work on layer 2 protocols and rollups and all that scenarios. We also have some products around in the fintech, supply chain, and other domains. And currently, I'm working with IOTA Foundation to build the next generation decentralized tech for developers, particularly in a project called Assembly, which I will also touch upon going forward. So, assuming that all of you are already aware of what blockchain is, I'll just skip ahead. Right. So blockchain, you obviously know as a decentralized network and a distributed database, right? But what would essentially classify as a decentralized app? You might be hearing a lot of these terms, Web3 and all that stuff. I don't know if I can move. So what does essentially classify as a decentralized app, right? First of all, there shouldn't be any central authority or server. So in a more traditional app where you deploy your say a backend on AWS or GCP, where you know exactly which server it is or server instance it is deployed to, or even if you're using say a serverless application with AWS Lambda and so on, still there's a certain virtual server which is assigned to which is assigned to you. So even if nobody can hack onto your servers, for example, if somebody just wants to bring down your entire product, they can just go and turn off the by chance if they turn off the entire the AWS data center from say North Virginia or someplace where your servers are deployed, your product is actually offline, right? You can't really engage with it, like your users won't be able to log in anymore, use it anymore. Which we have actually, which is very, very rare, obviously, because these are massive data centers with a lot of backups behind backups, and they have multiple power connections and all those things guaranteed to keep it up and running. But still, it is possible, and it has happened actually in just the last couple of years. You would have seen a lot of instances of this happen. And one of these servers goes down, the entire Stack Overflow is not accessible anymore. Slack is not accessible anymore, and a lot of these applications are not accessible anymore. So you might not be able to, even log into your or do your general work. That won't happen in a decentralized app, right? Because the nodes are obviously distributed. These may very well be also deployed on other AWS instances or GCP instances, but still they can be distributed across the world. You can even have your own server and deploy it in there. So that will also can act as a node to share that. That is one major aspect of decentralized apps, obviously. And the second is obviously distributed database. So that your data is also not at one single place. So if somebody just goes around, logs in from the backend and just tries to change a single data point in one of the in your database, that doesn't mean that your entire data set has now changed, because the same data also needs to be changed in all the other servers, or at least the maximum of the servers till the consensus is reached. So obviously, these are the very two main criteria that will identify something as a decentralized app or dApps as compared to traditional apps. So we'll just go through some very common terms that we will encounter in this talk as well, and as well as you might be hearing a lot of these. Web3, right? It's a general term to denote the decentralization of network and protocols. And it is also said that, from the Web 2 world where, most of us work right now, Web3 is just the next stage in evolution, where we won't be even, creating backends anymore. We will only be writing protocols from now on. And these protocols will serve, or, as smart contracts or whatever, and these protocols will serve as whatever functionalities that we want to work with in this Web3 world, right? Decentralized networks, right? So on the right hand, obviously, you can see what is a decentralized network. So basically, just doesn't need to be centralized at one point. That's all. And any blockchain needs to be decentralized. If I'm calling it a public blockchain and I am hosting all of the nodes, that still means that it is centralized at some point. It is obviously debatable that certain blockchains like Hyperledger, which is largely centralized because a particular entity is managing and has everything under its control. So I wouldn't term that as blockchain. If you want to make it a blockchain, you have to make it decentralized. And finally, what is exactly a blockchain? So just a regular chain of blocks, and each block can only be added from one point, which is the end node or in the end block. So each of these blocks will keep on adding one after the other, like a linked list, for example, right? There are some variations to blockchain in the decentralized network which has come on. One of them is called DAG, or Directed Acyclic Graph. So like blockchain is a linked list, you can think of DAG as more of a graph. So in a blockchain, every new block can only be added from one particular end. In a DAG or directed acyclic graph, it can be added from multiple leaf nodes, right? So theoretically, a DAG can be infinitely scalable, right? And one example of a DAG is the IOTA Tangle, which I also work with. So I'm not going to dig deeper into this. This is like this you can obviously go on and explore further at a later given point in time. But if you have any questions around it, we'll be more than happy to answer. And so far, we have seen immense number of decentralized networks which has come up over. I just checked. I think yesterday was 17,681 cryptos are listed on CoinMarketCap. Most of these cryptos, might not have its own network or chain, but a lot of these have actually. So most of these might be also, just a Ethereum variation, ERC20 token variation, and they are deployed on the same Ethereum network. But a lot of these will have their own network, their own set of nodes, and people working on them, right? Some of the examples that you can see in here, and I have like listed very less examples here, from 17,000 or more than 10,000 even, if you can think of. And these are think of these as like different networks, and each network will have thousands or millions of nodes. Just think of something like Bitcoin or Ethereum, right? So I have listed here only the networks which has a working smart contract or something that you can write more code on, as compared to other networks. Obviously, this is also not a very extensive list. There's a whole bunch of other networks out there. Recently, you would also hear about Solana and all that. But by the way, this is just the layer one, the layer one networks, or the base layer networks, right? There's other solutions that we will come into, that we will also discuss going forward. And so what has happened is every different network, now I can deploy, say, my dApp on one network, say Ethereum, but for example, somebody else here can deploy their dApp on some other network. But there is no way for us to communicate because these are completely different networks. You can think of this as way back before the internet, where every institute or every organization, they would have their own net, like intranet or something, and those will be like private networks, and the only way to communicate between two networks will be either to take out this data in a a hard copy format and then go on and run that over on the other network. Then there would be other problems which might arise, that this is a lot of time consuming. Then people came up with something like, how about we try to connect using a single protocol with this intranet and that intranet, and so on and so forth, and which led to the invention of what we work on today as internet, where everything is basically just one giant network, right? So that has not happened in the blockchain or the Web3 world yet. So that has given rise to a lot of cross-chain applications, and the need for cross-chain applications, because not one, like no particular one network is perfect. No particular one network has everything that you would want to utilize. For example, there's this amazing decentralized protocol on, say, Solana, and there's this other sort of application that you might also want to connect with, and that is deployed on, say, Cosmos or Polkadot. How do you connect these different applications? And that's given rise to cross-chain applications in particular. So what are exactly cross-chain applications? Any application that can operate across more than one network, we can define that as a cross-chain application, right? So here's an example of it. So for example, this on this side, you will see this is a blockchain X and this is a blockchain Y. Now, this is an example by using this product called Chainlink, which actually offers different chains to connect via defining a particular bridge that they work on. So what they essentially do is you can think of this as so what they essentially do is they will this is the application which is running here. This is the application which is running here. Now, what they will do is they will take out that in a particular format. They will transport that into that format to this particular chain, and then they will decode this in a format that this particular chain identifies with. So just to give an example, for example, this particular chain, like think of just as a simple, very, very simple differentiation. This chain, for example, identifies only JSON-based schema, or this chain, however, just identifies an X as an XML-based schema. The data might be just exactly same, but still there's a very small distinction, right? Now, if we send a JSON data to this one will be like, I don't know that data. So you would need to sort of convert it into XML. Now, this blockchain doesn't have any incentive to do that, but this bridge actually does that for us, right? Okay, now, and vice versa, like again, transporting from this chain to back to this chain, you will again have to transport the data. Now, this was just a file format change. Think of entire structural change. For example, in this chain, it is, say, your name is, again, a very simple example, your name is saved as first name and last name, and this chain is just a name, right? A name field, and both of them are just smooshed together into a single one. So it's concatenated into a single one. So then it's up to this bridge to actually convert that and send it. So you see a lot of this work that this bridge is doing is just transpiling things from one end to the other and just relaying that message. But that is very, very important task, because otherwise this particular network will obviously operate always in silo, and blockchains actually are very siloed networks where they still are only aware of what's happening inside this network. So they won't even be aware of if there's a real world entity or something else that is that action that they have to be aware of. So we build oracles for that, where a real world entity is actually introduced into a blockchain network and then is introduced, right? So this is a very simple example of what a cross-chain application would look like. All right, so let's move forward. And this has given rise to something called as interoperability. Interoperability is a concept that I'm very actively working on right now. And interoperability is a concept that that determines the interoperability of one particular dApp or network or protocol with the other one. And this is very crucial to building an entire network of various different of various different networks out there. So we obviously don't want to port over every application from Ethereum to, for example, Solana, or from Solana to, say, Polkadot or Cosmos, right? If for example, your application is deployed on Ethereum, you would very well want it to be there. But I have a Cosmos address, and my application is on Cosmos. So if I want to interact with something or exchange the data from your application, we need that feature of interoperability. That's why it's very, very crucial. There's certain different ways to, where interoperability actually came into being. The first thing is compatibility. So the first step to, making a cross-chain application work between various ones is to make it compatible with each other. Basically, have a standard de facto standard which a lot of which IEEE also defines, and certain other institutes like IEEE defines. And a lot of these networks follow the same thing. A lot of the protocols follow the same thing. And they would just say that, okay, you know what, we will all use the EVM to compile or to deploy our smart contracts, so that no matter which network, and this is just an example, by the way, no matter which network we are in, we can use the same Solidity smart contract. We can deploy it in Ethereum, in the Ethereum network using the EVM. We can go to Polkadot, and we can deploy it on Polkadot using the EVM. We can go to Assembly. We can deploy it in Assembly using the EVM, and so on. So they all are made compatible to each other now, right? So it just reduced one problem from a developer's perspective. Like from our headache perspective, we don't have to write separate smart contracts for each network now, right? So they're all compatible to each other. The next solution was obviously to create a de facto standard, which usually happens to be right now Ethereum, because it has been there for the longest, and a lot of developers very, very actively work on it. So it has essentially become the de facto standard. So one other way to let people create their own networks while having them to also work on a common stage, or a common environment, is to create the de facto standard that every chain will basically fork Ethereum, for example, and they will. And so, for example, I forked Ethereum, and we created something called as Indium network, which we at Acyclic use. Uh, we just changed certain amounts of these things, like we changed the consensus algorithm, we changed certain protocols to support fiat currencies and all that, but we are still using the same de facto standard. We are still using the get library to actually deploy and run our nodes. So tomorrow, if, for example, all our apps which is deployed on our network, they just say that, oh, you know what, we want to move everything to Ethereum, the Ethereum network itself. In that case, all we will have to do is somehow bridge it to Ethereum, or we can just ask them to write a migration script to take up all of this data and put it on Ethereum now, because all of this is obviously based on Solidity, based on smart contracts, based on the same transaction structure, the same transaction data. So all of this will obviously fit into the de facto standard, which is Ethereum right now. But the best solution going forward was to make them interoperable. So we don't need to do all that complex and the dirty work that goes around with migrating stuff, right? We can just make them interoperable, so that I can say that, oh, you know what, you want to use something on Ethereum, why don't you use this particular bridge, and you can still be on, say, Indium network, or our own network, but all you have to do is add this particular chain link bridge, and you can talk to Ethereum, or you can exchange data from them, you can exchange currencies, you can deploy something on them as well. So that was one of the most basic ways, or basic reasons why interoperability has been going forward right now as strongly as it has. This is another example of how that works. The image might be a little dark, but I'll try to say what exactly it is. For example, this is one DLT, this is another DLT. Now, these two DLTs doesn't even need to be blockchains anymore, because we are doing all of that in this interoperability node. Now, this interoperability node might be a protocol, might be a chain, might be a centralized or a decentralized solution. And there are obviously both types that exist today. And they will operate through this particular gateway nodes that we will connect to, right? And the only task of this interoperability node is to define the format of this particular DLT1 and DLT2, and just make that particular state transition channel, which then all of these nodes will use to exchange data. And that's exactly what interoperability is. Okay, so that was one part of this. Now, we saw this bridge here that got created, right? And this, I mean, there's a lot of bridges right now that is currently working on connecting different sorts of network out there. Okay? Um, there's some Tendermint focus bridge, there's some EVM focus bridge, substrate focus. Substrate is Polkadot's framework. There's some chain agnostic bridges and so on, right? But all of this have this one thing in common, that all of them are just focused on exchanging data in the best possible way, and that's all the bridges are doing. Some of these are very centralized solutions, so still you will have to at some point trust on these bridges. So what I mean by that is, for example, I have for example, I'm creating this one bridge, and say you would want to exchange data with, say, for example, somebody from here, or one of your professors, right? So you have, let's talk about just tokens right now. For example, you have 5 tokens that you want to transfer to somebody else on a different network. For example, say Polkadot, right? And on Polkadot, they are using this. They don't have it's there anymore. They have some other form of token, or they have a wrapped it or something. A wrapped is just nothing but just the same smart contract being deployed there and having to maintain the same sort of currency, but on that particular network. So that's what you call as a wrapped tokens, or wrapped any sort of cryptocurrencies that you would come across going forward. So for example, they have a currency known as ABC or XYZ, right? So now it is the task of my bridge to convert those 12 ETH to some form in the other to this XYZ currency, right? That's one way to do it. Obviously, you can just go to an exchange and you can do that. But that exchange, again, needs to be connected to that same network. So this bridge now has a lot of responsibility. Now you'll have to trust that this bridge will very honestly convert this 12 ETH to, say, 14 XYZ or 24 XYZ and so on. But what if I choose to, be dishonest, and I say that, oh, you know what, you have to convert 12 ETH to that particular network, but somehow, 11 ETH got lost, and I was only able to transfer 1 ETH to that network. And there's no way of obviously, verifying that, because I'm a centralized solution. Or I just admitted it. I'm not sure if that's what's supposed to be doing, but right, moving ahead. So yeah, that is one reason why bridges are so important, and they, at least according to me, there needs to be simply decentralized as well, because having it negates the entire factor that you have two decentralized network and they are connected by a centralized bridge, right? So it doesn't really make sense from having to go from a completely decentralized solution to nothing at all. All right. So here you will see how does a bridge exactly work. I mean, we already talked about it, so we can essentially skip this. But just to go over this image, because I had it. Any public or private blockchain network can be connected to any other public or private blockchain network using a bridge. So, for example, if an organization has a very private blockchain, right? And they want to now send over whatever transactions they have been doing to a public network. Now it's this bridge's responsibility to actually verify and validate the entire, or sort of in a way audit the entire network of this private blockchain, to make sure that whatever they are sending is actually true, and it's been proven, it has a proof attached to it, and so on and so forth. The risks are obviously much higher in a private blockchain network, because you will have to do the entire process yourself, and it's the bridge's responsibility to do that. So they have obviously a lot of responsibility from that matter. If it's a public blockchain connected to another public blockchain, it's actually very straightforward because all of the data has already been confirmed and validated by the different nodes which support that particular network, right? So here's an example of how this particular transfer works. Then there are existing bridges which does that. In this case, 0.1 wrapped ether is transferred to say that from ETH mainnet to X DAI chain, as I was explaining in the earlier example, from one blockchain from the ETH mainnet to say XYZ token. In this case, it's called X DAI token, right? And this here, once we transfer it, it will be called wrapped ether on X DAI, right? Because this is not just wrapped ether on the ETH mainnet, it is a wrapped ether on X DAI. Now, this particular value might differ by a lot more. So to give an example, your 1 rupee or your 100 rupees note in India versus what it will buy you in, say, US might be drastically different, right? So you might get, say, a coffee here at, say, for example, 100 rupees, but when you go to the US, it might still be like somewhere around 500 rupees, right? So you're getting the same content, but the value drastically differs. At the same time, if you look at from the other side of the how currency conversions work. So there I was talking about the value of a particular asset, which is coffee. Here, in like case 2, think of talking about the price of that particular currency itself. The exchange rate of how the entire $1 to say 72 rupees is determined is by the value of that particular currency, right? And that is the entire economics that goes on behind it. But you understand that the value that one particular dollar, that $1 will bring in different parts of the world versus 1 rupee that will bring in different parts of the world. That means these two can drastically differ. And that is the responsibility of, say, RBI or the other financial institutions to do that particular conversion, right? And give you a fair value of your currency. These are, again, centralized entities, and I'm not obviously picking on that any centralized financial institution just go away and replace it by decentralized entities or something like that. But this was just to give an example of how our current financial situation works as far as the transfer of a currency to another currency is there. So this is just for an analogy to what is happening in a blockchain-based network where multiple chains essentially exchange their currencies and in the same format. So 0.1 wrapped ether on the ETH mainnet can mean very, very different from 0.1 wrapped ether on XDAI. But for the sake of that particular conversion, it's the job of that bridge to get that fair value across different chains, right? So then it's up to the smart contract that is deployed for wrapped ether on this XDAI chain to determine whether your currency of 0.1 wrapped ether on XDAI, what does that correspond to for something else. So, for example, you are in Starbucks Seattle, and you are getting one coffee for 0.1 ETH on the ETH mainnet. But now you are, for example, in India, and they use XDAI chain, and you say that, okay, I have 0.1 ETH on XDAI chain, but that's not worth anything. So you'll have to probably pay 0.2 wrapped ethers. Now that's just wrong, right? Because when you transfer between cross chains, it's the job of this particular chain to actually admit what exactly is the right value for that particular currency. So that's why bridges have immense responsibilities and they cannot be centralized. All right. So, and the same thing can be extended across to exchange of data, exchange of NFTs, exchange of various different other things as well. So let me explain this scenario with an example of like usually I do this for to explain in very simple terms. So let me just try to do that. For example, we want to teleport somebody from here to, say, I don't know, another planet, or another, say, from Earth to Mars, for example. That's the simplest example I can think of. Say this is Earth, this is Mars, and here we use all these different types of currencies. On Mars, there is something else. Now, for one, if we want to, say, transport my own body from this particular place, from Earth to Mars, matter cannot be created or destroyed, right? The same, like some similar situation, currency cannot be just created or destroyed out of thin air. You have to take proper permissions from proper channels, right? So if I have to recreate myself on Mars, I'll have to probably recreate every atom by atom, molecule by molecule in the same particular structure till I get the exact replica of myself on this other planet, right? And with this particular replica, now I have two of me. One is on Earth and one is on Mars. Is that right? Because now there's two of me which exists in the same, say, a universe. So either I can burn this body in here, what on Earth I have left, and now I'll only live on Mars, uh, or I can lock this body up somewhere, or change or decompose this body's molecules to form something else. Now you might ask that why not fly myself to Mars? Because I mean, at this point we are in the same solar system, so obviously they will still require to breathe oxygen and all that. But for example, say Mars was a planet where you can only breathe nitrogen, for example, right? Or some other galaxy, some other solar system, and there you can only breathe nitrogen. So I'd have to modify my body functionalities in such a way that I can breathe in nitrogen and still for to survive. Now that obviously I can't do by transporting the body. I'll have to recreate that with those changes in the biology itself, right? And once I have created this particular body in this other plane of existence, now this particular body I can burn. A similar thing you can think of in two different networks. If I have to transfer, let's say, 1 million rupees in from, say, Ethereum to, say, Cosmos, right? I'll have to recreate or remine all of those tokens in the Cosmos ecosystem. But what happens to the 1 million tokens that I already had in the Ethereum ecosystem? I'll either have to burn them up, or the Ethereum ecosystem will have to decompose them or absorb them back into their, say, treasury or foundry or something else, and they can reuse those tokens in some other format. But I'll lose ownership of those tokens. Or which a lot of blockchains today do, is they just burn them up because there is no existence of that anymore in this plane of existence, right? You will also similar examples in NFTs. So if I have bought an NFT on, say, for example, OpenSea, and I want to transport that to, say, some other network. OpenSea is on, for example, Ethereum, right? and I want to transport that into some other marketplace, which is on, say, deployed on, say, IOTA network or assembly network. So in that case, once I create or mint this new token, which is the exact replica of this particular token in that network, I'll have to burn this particular this NFT, because now I will have two NFTs, just which just reduces the value, the original value of my own NFT. So it's in my best interest to actually burn these to actually burn these NFTs. All right, so I think that sounded a little more clear from what I was trying to explain. Right, let's go ahead. So what the problem with cross-chain applications now we'll come to talk about. I'm told that the Q&A is towards the end, but this is a considerably long session. So if I think anybody has any questions, you feel free to put it up on the chat and we can take it up. So cross-chain applications are now doing an amazing job, because now you can connect different sorts of applications from different networks and work together. But that has given rise to some of the very major issues with the cross-chain applications as well. One is availability. Sounds very simple and it's pretty straightforward, but what if this one network, like for example, you're connecting with one public network with a private network, and this private network is offline for, like, say, 8 hours of the day and it's only online only 16 hours of the day. What will, like, for those 8 hours, all these funds are just locked up and waiting for that chain to come online, and then only this entire bridging will happen. What if one particular network is down for maintenance? It's still a decentralized network, but it's down for maintenance or it's unavailable. In that case, again, this cross-chain application is still waiting, because these people are just ready to go. They just want to, use those tokens, do some processing on top of it, and so on and so forth. But now there's the other person who is on a completely different network is not even available to do that. A good analogy would be if you work with people from other time zones, right? You drop a message now to somebody in, say, the other side of the world, say San Francisco, and you drop a message now. It's late night for them, so they saw the message, they just gave you a quick reply, and they went to sleep. Now you saw the message, it's your daytime, so it's your work time, so you just keep on replying. But now for the next 8 hours, they are not available at all because they're just sleeping. And obviously, people need to sleep. So they wake up, they reply to you, but now it's your time to sleep. So now you reply quickly and then you go to sleep. And then they will be, working on something and they will try to connect with you. So this is a whole lot of issues with just time zones. And like the same thing can be, reiterated over in a general network sense. So one application in a different network will not know in any way if the other application, the other network is available or not. They will just try to connect and reconnect. They will just keep on sending this message till it times out, and then they'll be like, oh, you know what, this is not working out. Why don't you move to our network, or we move to your network, right? So there's still a very big issue in cross-chain applications, which people are facing today. Fee. You are doing the same work, but now paying 3 times the fee, or 3 different fees to be more precise. You are first minting, or you're first doing the same transactions or processing the same transaction on your network. You're paying the transaction fees on your network. Then the bridge is transporting your data to that particular network, and you're paying some fee to this bridge. The bridge goes to that other network, and that bridge does the same process on that other network, and that has some more cost to it, because again, you're reprocessing the same things on that other cross chain, on that other chain. So there is a third fee now attached. So while this sounds like a very good idea to, I'll be at my home, you'll be at your home, and we'll just send a package to you via Dunzo or via Swiggy or via, Blue Dart or whatever. But we now have to pay this 3 times this fee, right? I have to package the product. The parcel has to go via a delivery person. It will reach you, and then you will have to reopen it. Why don't we just move in and, the next door, I can just take the parcel and I can drop it at your home. We'll just reduce all these frictions. Will reduce, loss of data or any such issues. We can just, and the entire fees. This might seem like a very small issue if you are doing, very less on-chain activities, but for very, very busy applications, this is a huge, huge issue. Because like even $1 on every other network, you're paying $3. So if you had to do like a $1 million business, now you are spending $3 million for practically just trying to support cross-chain applications, which definitely doesn't make sense. So this is again one of the other big issues that a lot of products have been facing. And obviously interoperability. I'm on a blockchain, and that has no way to connect to the network that you are on. So if the bridge doesn't exist, there is absolutely no way that however more fees that we want to pay, however more available we both are, we still can't interact with each other. So that's still one, again, obviously big gap that cross-chain applications has, which is obviously interoperability is mostly solvable by bridges and everything, but yeah, it's still an issue. And the final is security. You still have to, like we discussed, we still have to trust this particular bridge to actually transport that entire data from one chain to the other. So that is obviously a very big issue from a security point of view. What if some data gets lost in between? Like, for example, in our sending a parcel example, I sent via Indian Post, and now nobody knows where the parcel is. That's actually wrong for Indian Post. It's not so bad, but you get the point, right? Or maybe during this transport, something gets damaged. It's a very sensitive item, and something is damaged. Your glassware has a small, tiny crack, which now is unusable. Similarly, in this case, you're transporting an entire, a whole lot of data, and in that entire hash, one single letter gets misplaced, or during encoding or decoding at certain point, they're using different algorithms or a different version of an algorithm, and the data gets corrupted in some format. Now the other person will never understand what you said. The basic issues with encryption and decryption, right? So this is some of the basic problems that cross-chain applications is facing today. To give a quick comparison, I'll just leave it on the screen for a bit. We have not talked in here about hash time locks, notary overcharacterization, notary credibility. We're only talking about bridging chains and the isomorphic cross-chain dedicated solution. All right, only these two. These are very, hash time lock has a lot of other issues, which I don't want to cover these. These are very, very big topics by themselves. These are mostly centralized stuff, so I don't want to talk at all. Bridges is something that I do want to talk about. All right. Just go through this very, very quickly. Now, we will dig deeper into the security aspect of it. I hope so far you're with me and everything is making sense. We'll go ahead. So security in decentralized protocols. When we talk about security, security is just not the only concern of decentralized protocols. Scalability is as well. So in some ways, there is few different. I mean, you obviously know the dilemma of solving the three problems in which you can only solve two of those, right? So either you can make either you can make the systems available, have huge data reserves, and make them secure, or you can make them very, very fast. So you will obviously have to, you know, choose or pick just two of these to make a proper system. So it's very difficult to actually support all of the three. So a lot of these security aspects or these security solutions that we will see has focused on two of these or sometimes just one of these, and they have gone ahead with it. So if somebody is focused on, the speed aspect, like the pace of transaction between two different networks or two different protocols, they have given up, or they have very less security, or they can't hold a lot of data between them. They can't process. They don't have a huge amount of availability of nodes, or they have focused on the security aspect of it, made it, very, very, very tight security based, very, very tight security. In which case they have given up on speed, or the other part is the availability and the storing of the data itself. Right. So each of these have their own pros and cons. We'll go in depth of. There are different concepts in shared security that we will go through. The first is called shared security. Obviously, the entire talk is on shared security. But shared security is a family of technologies that includes optimistic rollups, ZK rollups, sharding, interchange security, and so on. We will discuss what rollups are. We'll discuss what exactly each of these are. But so I'll just skip over shared security for now. We'll come back and we'll talk more in detail about shared security in a bit. The second concept that you will hear quite often is interchain security, right? Interchain security is a very Cosmos specific thing, which uses inter-blockchain communication, or IBC. Right. So Cosmos is another blockchain which has been focusing a lot on cross-chain applications. So in Cosmos, you can set up your own sort of Cosmos node, you can define your own transactions fees, you can define everything, and you can still connect with other Cosmos, other Cosmos nodes, other Cosmos chains, which is running on the same network. So they have focused entirely on the inter-blockchain communication aspect. So they came up with this interchain security concept, which just basically means that security is only handled in one chain. And if you have to transport data to the other chain, there's certain protocols that you'll have to follow very, very strictly. And then you can obviously do that. And third aspect is cross-chain validation. So cross-chain validation is what enables interchain security. So it's an IBC level protocol, inter-blockchain communication level protocol, and that will make sure that the data that you're transferring from one chain to the other is actually validated or being agreed upon by both the chains, which essentially is what a bridge does, but this is just a different way to do it. Bridges essentially set up their own nodes and everything. Cross-chain validation is just a protocol which will do that. There are other different concepts which we will not go in depth of. Cross-chain collateralization and shared staking. You might be hearing a lot about staking and as such. We will come to staking when we talk about rollups and all that for a bit, but you can dig deeper into this if you are particularly interested in cross-chain collateralization and shared staking. These are not very popular. These are not very popular security aspects that you will commonly hear in the Web3 environments or in the Web3 ecosystem. But there are some examples of some chains which use them. So now we'll dig deeper into shared security. In a nutshell, if I have to define the concept of shared security, it's just that how to make your data secure when you're transporting from one chain to the other chain, and make that trust provable, right? And also to make it fast enough so that the other chain is still there when this particular transaction is happening. Another thing that I skipped over because we didn't go through the introduction to blockchain stuff is that every chain will also have their uh, verification time as different. So what some chains can have 10-second verification time, some chains can have 7 days, usually don't, but can have. Some chains can have 5 seconds, some chains can have 15 seconds, maybe 15 minutes, and so on, right? So it'll also need to adhere to those aspects. So for example, if one particular transaction is taking a longer time to validate or verify, then we will just put it into back into queue and just plug it onto the next block which is going up, rather than rather than stopping the entire block from going, pushing to the network till this particular transaction is validated. So all of these aspects combined together is what shared security is all about. And again, I just want to iterate that is very, very much a research topic right now. So a lot of the aspects that you will hear today, as well as when you read further into it, uh, might and will change very, very, very quickly. All right, so let's dig deeper now. So the first way that a lot of people solved, the shared security aspect and also the scaling aspects is by using state channels. What exactly is a state channel? So state channels utilize multi-sig contracts. Multi-sig means multiple signature contracts to enable participants to transact quickly and freely off-chain and settle finality with mainnet. What does it mean? So for example, say me and say one of you. I'll just say Ram. I'm not sure if there's somebody called Ram here. For example, me and Ram, we just wants to discuss something, and the final result we want to announce, right? Um, so one way is obviously that we can discuss the entire thing in the same classroom while on this Zoom call, for example, and we'll be like, hey, you know what? This is what I'm thinking. Ram will come up with, this is what I'm thinking. Maybe there's a third person, say Tina, and Tina will say that this is what I'm thinking, and we will compare our notes. We will go through certain steps, and finally we'll be like, okay, this is what we conclude about it, and this is what we should be doing. So all of this conversation now happened on chain, right? Which cost us a lot of money. As compared to, for example, instead of, and also all of you will be waiting for us to finish our debate, then only you can go on to the next step that, okay, now we can talk about something else. So what state challenge means is that, for example, we just decided, all right, you know what? Hey, class, just wait up for a minute. We'll just take a sidebar. We'll just go to this other room, and we'll discuss in the side room our entire debate. We'll do this entire debate, and we went to the side room. We did this entire debate, and then we came back and we just said, okay, this is the final decision that we came up with. And we'll all have to do that. Um, it might sound sometimes okayish, or it might sound very, very wrong at the same time. How so? Well, if you want to also be a part of the conversation, you will have to go through that entire thing. But now, right, you can't, because all you are aware of is the final thing. So, what state channels means is that um, we will only post the final results in here. But the problem with state channels is that it's very application specific. So there are very specific types of state channels which is out there today. Like there is currently a state channel and a payment channel. So state transitions in every network for that, and payment channels. So if we have to settle transactions and just compare wallets and all that. And for every given state channel, like every given type of use case, you have to create a separate state channel. So, for example, this particular room is only dedicated to discussion of payment stuff. This particular room is only dedicated to discussion of, where do we want to go for vacation and so on and so forth, right? Now, this can become a huge problem. It is solving a lot of issues, by the way, right? It is solving the issue of very fast transactions. It is solving the issue of having it to secure the security aspect as well, because you know that this particular state channel has gone through a lot of audit process, has like you can blindly trust the state channel. So you will know that, okay, if three of us went inside, this the vacation room, we will come back with a decision of where we want to go to vacation. Or if we three went inside this payment room, then we will come back with a decision of who wants how much money and so on, and how who has to pay how much money to who. Yeah. So just for an example. But this can also be a huge issue, right? Because you will now have to create different state channels for every different type of use case out there, and which is increasing daily. You know, just look at different types of ERCs which is out there. It's just crazy how fast things are changing, how many different types of concepts are coming in. Today, you might just create a state channel for an NFT. Tomorrow, a new concept comes in, fractionalizing NFTs. Then you have to create a whole new state channel for it. So it's good from an aspect that if you already have it, you can just use it. But again, for every minimal small change, you'll have to create an entire different state channel. It's a huge headache. The next solution that people came up with is side chains. Now, this is more of solving the scaling issue than the security issue. But let's just go through it because we will need to take an example of sidechain in the when you're talking about next thing. So what a sidechain is doing is it's an independent EVM compatible blockchain which runs on the mainnet. And these are compatible with even two-way bridges. What it means is that I hope a lot of you have heard about Polygon, right? So Polygon is a side chain which runs in parallel to Ethereum, and it does a lot of these transactions on its side chain, and then you can just deploy the final thing onto the Ethereum mainnet. From a scaling perspective, this is very useful because now you don't have to do a lot of these transactions on the main chain. You can do it on the side chain. So we can essentially, get onto a separate classroom, not a side room, by the way, just a different classroom, and we can discuss on there. And any of you who would want to listen in, because in the state channels, only three of us, only the decision makers would be there. But now anybody who wants to listen, this can come just to the side chain and they can follow the entire debate, right? So if you want to listen to the entire debate, come to the different room and you will be able to do that. And if you don't want to, just sit on the main room, and once we are done, we will again come back and pose a solution. So this solves the problem of security on the sites itself, because these are again EVM compatible, right? And they need to be compatible, because otherwise you will write a separate smart contract for the mainnet, you will write a separate smart contract for the sidechain. Nobody will do that. So people just will stop using this thing. And since this is a separate blockchain, now between these two blockchains, we need to build bridges so that they can talk. And it needs to be a two-way bridge, because we need to send all the transaction, all the data from all the inputs from the mainnet to the side chain where everything will be processed, and again back to the mainnet once things are done. Certain kind of applications might also ask you to submit proofs along with the final result from the side chain, so that they can also verify if need be. And you can also verify things on the side chain if ever some situation arises, right? So if you want to later look into this particular debate, you can go on to that other room, and there is a recording of theirs available where you can just sit and just listen to the entire debate later on at a given point in time. So that's particularly what sidechain is. A sidechain may or may not have a different set of consensus rules. It's completely up to them. It may have a different set of block parameters. For example, on the mainnet, we were only supporting, say, 10 blocks at a time, or sorry, 10 transactions in a block. As a sidechain, we might support 100 blocks in 100 transactions in a single block. right? We might have a different set of consensus. Even on the main net, we might have some proof of work, which right now Ethereum is. On the side chain, we might have proof of stake, just to speed things up, or proof of authority, or proof of burn, whatever. Like there's different types of consensus out there. So there can be various different types of. We can configure our sidechain in completely different way. Sidechains can also be very, very private chains. So that is also possible if everybody on your network validates that, okay, fine, we will be using, we can use private sidechain. So that's completely fine until and unless you post the main thing on the main net after the task is done. So that is also a very, very big possibility for sidechains. So now we'll talk about rollups. I hope so far everything is clear. If I'm going too fast, let me know. If things are getting very, very complicated, let me know. If things are way too advanced or not advanced enough, also let me know. All right. Moving on, we talk about rollups. So far we have seen two different types of examples. One is we go to a different chain, or we go to a different state channel, right? What if we don't want to go to a different channel or to a different small room? What if we just want to step out of the door in the hallway, discuss this very quickly, and come back, right? That's what a rollup is. So a rollup performs transaction execution outside of layer 1, and the data is posted to layer 1 where the consensus is reached. What does it mean? It means that any processing that we'll be doing outside of this layer 1. So we'll not do it on chain. So we'll do all of this processing outside, like in the hallway. We'll just discuss quickly, and then we'll come back and we will take a vote of the different options that we have, right? So, and this will be done by every different nodes, right? So I will go into outside of the hallway and I'll come up with my own solution. Somebody else will go up in the hallway, they'll come up with their Ram will go up in the hallway, they'll come up with their own solution. Tina will go to the hallway, come up with their own solution. We come back, everybody will come back together and we'll compare notes, right? That's exactly what a rollup is. Also, you can take another example. Say we have to decide on what is a function is like a multiplication function, and it says what is 3 times 9, right? So when you break down that particular statement 3 times 9 into say opcodes or assembly language itself, it will be like multiple different lines, right? And at the end of the day, it can be just think of like if we are breaking down into our compiler is breaking it down. So that can be 3 times 9 can be okay, what is 9 plus 9 plus 9 3 times. We are adding that number and we are reaching how much is it, right? So that particular part of that function I'm doing outside of the chain. And I'm going back and I'm saying that, okay, 9 plus 9 plus 9, it's 27. Somebody else comes up with a different type solution. All right, 3 times 9, what I'll do is I'll use a different sort of algorithm. I'll just add 3 9 times. And then they go out, they add 3 9 times, they come back and then they say that, okay, you know what, my answer is 27 also. So, okay, we agree. And the third person goes out and then they'll be like, okay, I'll do 9 plus 9 plus 9, but during this processing, they do something wrong and they come back with an answer of say 26, for example, right? By mistake, they did something wrong in their calculation. Obviously, this is a very simple calculation, but you can think of that as an analogy to a more different or a more difficult sort of problem, right? So they come back with an answer of 26. So now we compare notes, and I come up with okay, my answer is 27, somebody is 27, somebody is 26. There's a consensus on chain, we reach that, okay, 27 wins. So 27 is the right answer, right? That's what basically a rollup is. And these are very, very important in terms of, say, securing the native Ethereum itself, because since we are doing the consensus on chain, all the security that the on-chain governance offers still remains valid, right? Only the processing is outside, everything else is on-chain. So that's why rollups are so important to learn if you're getting into the security aspect in decentralized applications. And there are different types of rollups. The first is called optimistic rollups. As the name suggests, we are very optimistic about it. What it means is that optimistic rollup says that everybody is good until proven guilty. It's also something that our government says or our legal system says, but that's fine. So everybody is very optimistic about it, right? So we will accept all the answers that everybody comes up with. So if you say if you say 3 times 9 is 27, we believe you. If you say 3 times 9 is 30, we believe you, right? But then unless somebody complains, somebody comes up and says that, challenges that, says that, oh, you know what, this person is a crook. He's trying to squeeze in the wrong amount or the wrong value or the wrong data into the chain somehow. So then they will show a fraud proof of that, right? They'll say they'll point fingers and they'll say that, okay, this is a fraudulent transaction. Now, once a transaction is marked, what will happen is optimistic rollups, what they will do is they will just take that transaction, they will run the entire thing on chain now. That will obviously cost a lot of money, but if proven that, okay, this is a valid proof, then a valid fraud proof, then what people will do is they will, like, it enters so everything that particular node would have staked by that time will be slashed. So if, for example, so you can think of that as a fine of trying to push a fraud transaction into the network, right? And maybe the other person who has reported this might be rewarded or might not be. That depends on the on-chain governance and all of the aspects of it. But from a security aspect, optimistic rollups is very, very insecure, because we're just saying that everybody is welcome unless somebody complains that you're not welcome inside, right? So that's what an optimistic rollup is. The second type of rollups is called zero knowledge rollups or ZK rollups. These run computation off chain. So I'll do all of the computation off chain, and then I'll come back and submit with a validity proof, right? Okay, this is my proof. For example, you prove your theorems in maths, right? And you go out and you write a particular proof for, say, Euler's theorem or something, and you come back and you show that proof, and you say that, okay, these are the steps, and because of that, it's proved. Now, this obviously takes time, because doing the entire computation off chain, coming up with a validity proof in a particular format, and then submitting it, obviously takes time, but it is very, very secure. Zero knowledge rollups, ZK rollups, does these computations off chain, and it can be trusted because they work on something called as zero knowledge proofs itself. Zero knowledge proofs is entirely a different topic. I mean, it will be a very, very big topic. So I would suggest that you read it offline by yourself, and definitely do read it if you're not aware of it. It's very interesting, by the way. So ZK rollups are obviously secured by the ZK proofs that it comes up with. But so from a security aspect, ZK rollups are very, very secure, right? But another issue is that these are extremely slow, because you're doing everything off chain and then you're coming back and you're submitting it. So essentially, I'll have to wait for a considerably longer time until you come back with the validity proof. And this is not done by just one node. This is done by every node. And then every node will come back, submit the proofs, and then proofs will be compared, consensus will be reached, and then agreed upon or something, right? So that is what ZK rollups is. One thing about optimistic rollups is obviously very fast, but the withdrawals is extremely slow. What it means, why? Because while I trust everybody that, okay, everybody, can just come in and join this. Like, for example, this Zoom meeting, a lot of people are just coming in and waiting in the waiting room. So everybody's welcome to click on this link and come to the waiting room. But then I decide, or the organizers decide, the professors decide when to allow somebody in, right? If somebody is in the middle of something, they might not allow at that time, or maybe not in the middle of the class or something. But you're free to come and wait in the waiting room. That's what an optimistic rollup does. It will say that everybody is welcome. The transaction has been accepted, but it will let you wait for a period of, let's say, 7 days or something, till so that time is necessary that to give to all the nodes to agree upon, so that it will just make sure that nobody has any complaints with the transactions which is waiting in our waiting room right now, and then everybody can let them in. Similarly, for example, let's say in the Zoom call, say for example, somebody just comes up and waits in the waiting room. Now all of us here, we decide, okay, should we let them in, and we take a vote. If everybody votes, you say, for example, you don't like somebody, and you'll be like, no, you know what, don't let them in. And if the majority of the people don't like them, maybe they don't get in. So that's what, as a democracy. So that's what a consensus exactly means, right? ZK rollups, on the other hand, because they have a validity proof attached to it, they can be just forthright. Like you can directly, let them in. So if somebody has, as an analogy, if somebody has the right credentials, you just let them in the door, no matter what the existing. And after that, you decide whether to keep them or do whatever with them. So that's the difference between optimistic rollups and ZK rollups. Oops. So this is the kind of part where shared security comes in, and shared security aspects starts from here. So far I have given you a primer of what shared security is and how it functions, how it works. We will be using some sort of rollup, either one or two, to secure, to prove that our data on the off chain and on chain, to compare that and to give validity proof around that, to put it up on the network. We will also use the same sort of mechanisms on the bridges itself. So while building a lot of these layer 2 solutions, you will have to keep in mind that the shared security aspect of it lies exactly with these proofs. There are different types of other rollups which is coming out right now, like Arbitra, Boba, and so on, which has done a certain number of modifications on top of these original rollups. So we need to speed up things a bit, obviously, because ZK rollups, while they are secure, they are not very fast. Optimistic rollups, while they are very, very fast, they are not so much as secure. Or even if they can be secure after the period of 7 days, 7 days is a long time for somebody to wait for their withdrawal, right? So that is kind of the stage that we are in the shared security space, and there's a lot of work is obviously going on, which will come up in the next, hopefully the next few years, which will have a more clear structure of what shared security can be. One of the work is also that we are working on at Assembly. So, I'll let you discover what Assembly is and what we are working on so far. Essentially, Assembly is basically something that is like a cross-chain application or a network that will work on top of the existing blockchains or solutions, and will give us certain advantages over traditional blockchain networks, or over something like a cross-chain application network like Cosmos and so on. That's what Assembly is doing right now, and we are working on this as we speak. So if you have to define it, assembly is a permissionless protocol to build, connect, and deploy smart contracts on a keyless multi-chain network. That's exactly what it is. On assembly, you can deploy different nodes. Each node, you can deploy multiple chains. On each chain, you can choose which VM to go with, Wasm VM or the WebAssembly VM or the Ethereum VM and so on. So this is something that is currently on testnet and the beta is out. We're working on towards putting it up on the mainnet soon. Sorry about the background. There's seems a lot of light is keeping through. Anyway, so yeah, do check out assembly and let me know what you think about it. With that, I actually come to the end of this talk. And if anybody have any questions, we can go ahead and ask it.
Participants, please feel free to ask questions. You can post your questions in the chat box, or you can ask the questions directly. The mic will be provided.
This was a considerably long session, but I hope everybody's still awake. If not now, feel free to connect later and ask your questions later. We'll be more than happy to talk more about shared security and decentralized apps and kind of work that we are doing right now on it.
Thank you so much, sir, for your valuable time and enlightening us with your magnificent session. Thank you so much.